in the previous class I had actually drawn the transition matrix after step 1, okay, for any switch in stage J, and from there of course then I also wrote the equation. So probability that after step 1 you will be in state I in stage J in time slot tau k in this time slot. This will be given by, if you know after 0th step or just before beginning of first step or the third step of previous time slot, okay, after that whatever is your state, so you have to get that probability. So if you are in state M, okay, then we need to actually multiply by all transition probabilities, basically it is a row, basically the whole column. So this will be T, this is the same matrix which I had written earlier, this is for stage J for transitioning from M to I, okay. So for whichever things these are Tj1, Mi is 0, those transitions are not permitted actually. So only whatever are the valid, those have to be used. You will know this probability and you can always estimate this one, and this summation has to be over M is equal to 1 to 14. This computation will be required.
It finally will converge to some value. So what is the convergence condition and which value we are there?
This is from P0 you will find out 1. I am going to come to convergence condition actually. Okay, that's a steady state operation technically. Steady state is stable operation, that's only we need to identify. Okay, so now let's come to the second matrix when we will go from state 1 to state 2. Sorry, whatever is there at the end of step 1, we have to go and find out what will happen after step 2. So what is the transition probabilities in that step 2 actually. So we will actually put that, and that will be written as T2 J. So only thing, the superscript will change from 1 to 2 because a transition which is going to happen in the second step. So let me build up a matrix here. So I am just going to put a 1 by 1. So if you are in state 1 for example, remember in step 2 what happens, only the packet from input to output actually that movement happens. Now there is no packet at the input, so no packet can go to the output, so next state has to be only 1, and that will happen all the time. Okay, so I have to put only 1 here, rest everything will be 0, so I will be keep on, I am just putting the entries which are existing, all other entries will be 0 in the matrix. Now look at the state 2. State 2 there is no packet which can go from input to output. So after step 2, just before after step 1, if you are in state 2, step 2 will not make any difference, you will remain in only 2. So there will be 1 here in this case. Look at 3 now. So same is true for 3, you will remain in state 3 only. Look at state 4 now. Here, if you are in this state just after step 1, certainly this packet is going to move, and once it moves you will go into state 2, and that will happen with the surety. So you are going to put a 1 here, all the entries will be only 1, and that's an important thing. There is nothing like half or something, because there are no exit and incoming probabilities. Pj bar and Pj tilde are not participating here in the step 2 actually. So the fifth one, so fifth one will remain in fifth, so 4 nothing will be coming, fifth one there will be a 1 here, okay. Sixth, there will be a movement out and you will end up in state number 3. State 3, I think that's where you will come from 6. Okay. State 7, nothing will happen, you will remain in 7. State 8, you will come to state 5 actually. Fine. If you are in state 9, both of the packets will move out, you will come to state 3. State 10, nothing will happen, you will remain there in state 10 only. State 11,
7.
you come to 7 actually, right. State 12
Again 7.
is also 7. State 13, you will remain in 13. State 14 will remain in 14. So you have to just put somewhere a 14 here. I don't have the space, so I can put a 14 beneath. This will be a transition matrix for after step, and I can again write down the equation. So what will happen after step 2, you will be in state I, in state j, in time slot k, will be given by whatever was the probability after step 1, transition matrix 2 in state j from, this has to be m, so this will be a
this equation comes actually.
See, probability that you will be in state 1 is given by this, and this is the transition probability you multiply. So in 1 how you can come in what always, for all other values it will be 0. So probability of being in state 2, even if it is there, but these transition probabilities are 0, does not matter. Similarly, look at what is the chance that you will be in state 3, for example. Okay, state 3 is here, I is 3. So 1, 2, 3, transition is 0. So only thing 3 to 3 you will come. So then there is a, what was a, after step 1, what is the probability of being in step, this is state 3, that has to come in, because that comes that way actually. If you know the probability of being in state this, multiplied by transition probability, you can be in this state. So you can be in this state through this route, through this route, and through this route. So sum up each probability into transition probability into transition probability into transition probability. Sum up all these are all mutually exclusive events, will give you probability of being in state 3 after step 2. Okay. Third one is, similarly we will have third actually transition matrix. This happens because of step 3, which is arrival into your incoming ports or incoming buffers. Okay. So I will just draw it on this side. So I actually have a superscript 3 in this transition matrix. So if you have to go to 1 state, so 1 to 1, remember it's because of the arrival process. If you are in state 1, there are possibility that one packet will arrive, there is a possibility 2 packets will arrive at both the lines, and there is a possibility no packet will arrive. If one packet arrives, so Pj bar and Qj bar you have to use. There are 2 possible ways. Okay. So first thing, Pj bar, let the packet be there, packet arrives actually. Pj bar is square, both packets will arrive. So what will be the state if both packets will arrive? It's only arrival process, no departure, no transmission from input to output. So you will end up in a state 9 and 8 both with equal probability, remember. 8 and 9 both will equal probability because they may be directed to any one of those situations. Na? So you have to write now so 8 and 9. So this will be Pj bar square, half and half when both packets are arriving. When only one of them is arriving, then what will happen? You will always get in end up in 4. So here you have to write 2 Pj Qj bar, and if none of the packets arrive, you remain in the same state. Similarly, state 2, you can have no packet arriving, you will remain in state 2. If one packet arriving,
5 and 6.
it will be either 5 or 6. So one packet arriving probability is 2 Pj Qj, both bars. I am making half of that. And next one, both packets will arrive.
3 states.
Okay, both packet will arrive. So there is one packet here. So both packet will arrive. One possibility, they both are directed here. They both are directed here. One is directed here, one is directed here. Yeah, one is directed here and one is directed here. Okay. So this one is corresponds to which state? 10. And next one corresponds to
12.
right. This will correspond to 12. This one will correspond to 11. The next one also corresponds to 11 only. Yeah. Fine. So the probability for this is both are coming. Pj square is 1 by 4 Pj bar square, 1 by 4 Pj bar square Pj bar square. Agreed? So this is what all actually has to be put here. It will be 1 by 4 . 11 will be 1 by half. Similarly, for item 3, I think now should I leave or should I verify everything? I can write down, I think, all the things and you please verify. Okay, that will save time. I think now you know the method how this has to be done. That is more important. So look at item 3. I think whatever is clear, I will just keep on putting. Wherever there is some explanation required, I will do that. Or actually, it is not required. It's possible. 3 to 3 qj square bar 7 and then 13 and 14. This is from state 3. Yeah, that's the way I think I can join them. Eight and 9. Now everything else will be diagonally unity actually. So only initially you have to do some calculation, rest everything is pretty simple after that. So this will be the third transition matrix, and from here you will actually get the third equation, which will be what will happen after and this will be nothing but equal to P0 I j k plus 1.
Sir, how it is going from 6 to 13, sir, with half PJ?
This 6 to 13.
Yes, sir.
6 is only one packet can arrive.
Yes, sir.
If there is no packet arriving, you will remain in a state
6. 13, sir. 6 to 13.
It's only arrival process, no going from input to output port, remember, okay. So you will remain in 6. If a packet arrives, then this packet can be directed to any one of the ports, outgoing port, any arriving packet.
Okay.
Direction is also important. So there will be 2 packets at the input and 1 at output. So you might actually end up in choosing either this
11 or 2.
a packet coming, either this will be there or this will be there.
Why not 10, sir?
13.
Why not 10?
Okay. See, this is a situation. 6 is this actually. So if a new packet comes, this packet can come here. It has to come here only, there is no other option. And once this packet is here, this can either be directed here or there can be an equal probability of this being directed here.
Sir.
There is no other possibility.
No, sir.
And this is nothing but, if you twist these ports, but 11.
There are 13 entries made, sir. For 6.
Just hold on. 12 and 13. Yeah, it is 11 and 12, you are right. I have made a wrong thing. It's 11 and 12, rightly picked, I think. That's correct. Perfect, you are right. So this is clear. Now important thing is that when I am looking at what is going to be the state probability after step 3, that is nothing but after step 0 of k plus 1. Okay. So step 3 in kth slot or tau k is nothing but step 0 in tau k plus 1. So now I have got the transition state probabilities for the next time slot. So through 3 iterations. Now the method which actually is followed, we also define something more here. This is there in the paper actually, you can even just make a copy from there. So if you cannot note it down, you can just. So we define another probability Pj. So we have defined Pj bar, Pj tilde, and now Pj, the last one. It is a probability that packet exists at an output link of a switch in stage J at a time tk. I am not talking about interval, this is at time tk, because after time tk the first step will start, then step 2, step 3, then tk plus 1 comes. So that's why I was using all the time in earlier definitions interval tau k, and I was defining a step because step can finish at any point of time. But here it's, this will be only happening at the slot interval. Okay.
Multiple of the minimum.
Yeah, always. Because there can be situation your see analysis wise or what we call computational model, can only be created for when T select and T pass, either one of them is 0. That's why we have done the computational thing. When you take, for example, T pass is equal to half of T delay and T select also half of T delay, is going to be slightly complicated in that case. So paper actually only does a simulation thing for those cases, and computational model is used only for the two extreme cases. Actually result will be somewhere midway in between the two extremes. So this probability will be given by, you can look into the states and find out state 1 does not come into picture, there is no packet. If you are in state 2 with half probability, you will have a packet at an output. Okay. Remember, I am using 0 now here. Okay, stage J, time step K.
You can also use 3k plus 1 in this case.
TK.
That's fine, it's all the same. 3k minus 1. 3k minus 1. I am assuming that it is for k. Pj will keep on changing, remember, and I have to keep on computing till Pj stabilizes, because in the beginning I will be starting with the extreme thing cases. Okay. Then you have only fifth state where there will be only one packet. Just you list all the states where there is only one packet at the outgoing port, and then plus without half all the states where two packets are there at the outgoing port. Okay. So 2, 5, 6, 10, 11, 12. And when both of them are there, it is 3, 7, 13 and 14. So now the procedure actually of this.
What is the difference, sir? Tau k and tk?
Tau k is the whole interval from tk. If this is tk, this is tk plus 1. This interval is tau k. Tk is the instant, is a time instant. So what will happen at tk, all switches will be in step 0 or just before the step 1. They all will execute step 1, then they will all execute step 2, step 3, one by one. So you will actually can, if you can visualize, it's kind of, remember when you are running 1 here, 2 is running in the back, next stage 3. So from output port it will be flowing backward actually. So this will go to 1, then next one will go to 1, so this will move to 2, then this will move to 1, this will be 2, this will be 3, and so on. And once the 3 is done, then it will be 0 for the next step. So there is no execution after that. So in your computation you are just running like a wave actually of 3 steps from forward to backward direction. So all 3 will be iterated, then next time slot will come. So computationally it will be that way actually.
So why we are interested in this probability?
This is actual probability because the throughput performance will be computed from this. Pj tilde will not give you. Pj tilde is a conditional probability. If the packet exists, then it will go out, that is a Pj tilde. If a vacancy exists at the input, a packet will come in, that is again a conditional probability. This is absolute probability, because all state probabilities are nothing but absolute probabilities which we are handling. That is why denominator numerators were actually computed, because they were conditional probabilities.
This will give us absolute throughput with the help of Pj. We are
This will not give absolute throughput. Pj dot Pj tilde. So this is a rate at which the packets will be going out from a port, and this will be same because no packets are being lost. So technically incoming rate has to become equal to outgoing rate. This will be used as a test actually during all your iterations. When this will become same for all stages, you have stabilized. Now things cannot change anymore in your computation. At that time you just measure what are the state probabilities, and once you know all that state probabilities, you know this also, because from those state probabilities you are anyway computing Pj0, Pj and Pj tilde. So everything is stabilized, and now you know now you know this, you know Pj tilde, you can find out the throughput performance from here. Take any stage, does not matter, this will be same for all stages. This will become independent of J. In the beginning it is not, because there is a transient in the system. So that will be the check for essentially convergence. Oh sorry. It has to be P0. It has to be P0, right. So let us come to the procedure. I have verbally told it, but let me just write it down step by step how it happens. So what we have as the boundary condition as 1 or 1.0, whatever way, P0 bar is going to be 1. These are two boundary conditions which will be used. Initially, when there is no packet in the system at time t is equal to 0, I can get some kind of initial values are required for the state probabilities so that I can iterate. So all state probabilities at t is equal to 0, all of them will be in state 1, will be 1 for all j's, for all stages. There is no packet in the system. For all j, and m is greater than equal to 1, greater than equal to 2, and less than equal to 14. That is the initial condition. So first you are going to find out and for all j. This is the first step which you will be doing. You will find out this thing for all stages, which is viable, okay, and then you will compute for all stages So with these conditions you will find out then P2. Remember transition matrix. Every time you are computing transition matrix based on the probabilities, you know the earlier thing, so you can always find out using those equations the next step. From there you will get now again for this, and this will be nothing but will become equal to P01 mj. Go back again, iterate, keep on iterating this thing, and you will keep on iterating till you will find that your Pj dot Pj tilde, alternatively for all j's this should become same. some constant k, it will just achieve some constant k value. This is the throughput per port actually, is a fractional utilization of the port.
Sir, just could you repeat, sir? We have done this iteration, sir.
Huh?
We keep on doing it.
Keep on doing it.
Right, sir.
After some iteration, you will be all the time observing this value also. Every time tk, you will estimate what's the value of pj and pj tilde.
But in this iteration, you are not calculating pj tilde.
pj tilde is dependent on the state probabilities, remember. So every step you will be computing. You are going to compute the matrix, you are going to compute the transition probability matrix and those pj tilde and
pj bar.
pj bar for all stages. This has to be done iteratively every time. And this you will keep on doing till you find this value is turns out to be constant for certain number of computations. So paper actually does it for about 100 iterations. It should see the same value. Actually it will be always converging all the time, minor correction. But if it's going to happening at the 10th decimal place, you don't bother further actually.
You get in graph and you plateau.
Yeah, with time actually if you plot, you will stabilize. That's the convergence of the algorithm. And once you converge, you have achieved the values. Now you know all state probabilities. You can do whatever you wish now with it. An important thing, these initial values are fine. This pn minus 2 tilde is 1. If you change pg or bar is equal to 1 from there to some other value, you can even change the load factor, incoming load factor. So this for maximum loading condition when it is 1. You can make it half also and then start doing the computation. Then also you will get a throughput. So throughput versus load also can be done by getting various points.
So then it will not maximum loading.
That's not maximum loading. Maximum loading is when P0 bar is 1. Okay.
So why you choosing only 100?
That's a paper this guy must have observed after doing computation. For 100 it remains stable, it does not matter. Then mostly it's basically by observation.
100 for what value of n?
And there is no n here.
He done it stages wise.
See, size of switches does not matter now. Size of the switch is now being reflected in terms of number of stages. The number of ports you don't worry, is the number of stages what matters. And since it's a delta, is a buffered delta or buffered banyan actually whatever it is, because it does not matter whether it's delta or not a delta here. I have not used anywhere anything related to routing. What I am stating is there are two inputs, both inputs should be independent of each other. That's the assumption which we have used. This input, arrival at this input and arrival at this input are independent. Departure at this and departure at this are independent. And this will happen if they are always connecting to always disjoint sets, which is true in I think banyan network. By design actually that is true. If there are no loops, there is exactly one path between any input and output port, this will be satisfied. So this result is true irrespective of the topology. Okay. So this is what has to be done. For all j's, this has to become constant, and after this you can actually find out the throughput. So throughput will be what? So throughput will be, now remember, is pj dot pj tilde, that's what is going to be constant, but pj might be different across the switches. Pj will be different across the switches, across the stages, because if the pj is higher, you will find pj tilde will be lower. As you go across, pj will be going down and pj tilde will be increasing as your j increases actually, but this relatively will become, product will become constant. That's a flow rate. So whatever is incoming has to go out, that's what the condition basically. So there is no storage in the switch, so switch is stabilized now in a stabilized condition, because you are starting from your initial state is all zeros, there is no packet in the system. So it will start storing packets actually, because there are buffers inside. So once the storage is stabilized, this condition will be satisfied in that case. Okay. So it's like if you have, for example, a water is flowing, you have a tank and then tank is going out. So this buffer, if tank is empty, the rate here will be higher, rate here will be lower. You can build up a cascade of this. Technically is nothing but something similar. Another tank, another thing. So find out flow rate here, find out flow rate here, find out flow rate here. You will be in steady state when all these three flow rates are same. And this is nothing but flow rate.
Flow rate per port.
Yeah, flow rate at the output port of every stage. This has to be same. And flow rate is same at all ports does not mean that your PJ will be same at all ports. PJ's probability that packet exists. So this will always be higher for the initial stage or the input side, and it will reduce as you move to the output side. And PJ tilde will be reversed, so they both will stabilize. So one will be actually decreasing, other one will be increasing. This product will become constant.
There
Okay.
is no relation with PJ bar in no relation with PJ bar.
PJ bar also, if you want, you can push. What will be the flow rate for PJ bar? It will be, I will say QJ. QJ bar. Sorry, PJ is the packet. QJ packet is not there, and packet arrives. That's the incoming port side flow rate. This has to be constant across all J's. That is also fine. This also is a flow rate. For all J, if this is going to also become constant, then also you have converged. That's the equivalent condition symmetrically. And you can similarly look at what happens. QJ will be smaller on the input side stage, stages which are closer to input. As you move towards output side, this QJ will start increasing, while PJ bar will be smaller in the input side, and it decreases actually as you move. It will be higher, it will be decreasing as you move towards the output side. So I can write there it is PJ bar or yep, PJ on this side, this is nothing but PJ tilde or is a pairing basically.
Sir, what is the guarantee?
So if you want to
converges?
take, you either take this as a pair or you take this as a pair. Under stable conditions, their products will become constant. You were asking some question.
Sir, what is the guarantee of convergence? Although we say that one is increasing and
Mostly it's a first order
but we
system.
do not take any consideration the rate at which one increases or decreases.
This is only a intuition. Actually, honestly speaking, I don't have the proof whether it will converge or not. But since it seems to be like a first order system, there is no second order. So if you make a difference equation, you don't get a second order difference equation. You get actually first order difference equation. That's why I think it should converge. Well, that's my intuition. I have not verified that. Anything which is first order usually will converge. Only second order will actually show the oscillatory behavior or resonance conditions and under which the convergence cannot happen. Only important, yes, if it's a first order, your decaying coefficient has to be negative. If it is positive, then it will explode, then also it is unstable. But instability cannot happen because the probabilities are bounded from 0 to 1. Because what happens in this case, this is what we call total things are conserved. There is a principle of conservation actually being used here, honestly speaking. The total sum of all possible events which can happen mutually exclusive, sum of probabilities will always be 1. So once probability increase, others one will go down. So you cannot get that case of exploding to infinity in first order system. So this first order system also cannot oscillate because since it's a first order. So only possibility existed, this first order will always converge. So intuitively I know this is the way it's going to happen. But I think exact way is you build up actual differential equation as time evolution happens, and based on that you make a judgment. Now that will be the more sophisticated and better approach to prove it. Paper does not talk about it. I think again the paper, the author has done it through this intuition itself, and once the intuition they are satisfied and they have seen it happening, they assume their intuition is correct, they never tried verifying it formally. So once you have this, you can now build up what we call the throughput performance. Let me write down the throughput is what it will be. So what are the chances that packet will be there at the n minus second output port of the n minus 2 stage, and if this packet exists, this packet will go out immediately, this we know, okay, because pj tilde of n minus 2 is 1. So that is why we have taken, actually I have to always find out this flow rate. Take this flow rate, this is what is going to be transmitted in 1 t delay, and that is what gives you the throughput, and total number of ports will be 2 raised power n divided by t delay. Alternatively, if you want to put in terms of j, it will be under steady state condition, this will become independent. For all j's, this value will turn out to be same because this is constant all across, and pj tilde is nothing, for j is equal to n minus 2, this will be nothing but p of n minus 2. Okay. So this is what I am using, and this is what gives you the throughput performance. And what's the maximum throughput which we can get?
Pn minus 2.
2 raised power n packets per t delay which can be moved out. Okay. So that's the maximum which you can get when Pn minus 2 is 1 actually. So you divide by the maximum possible value, that gives the normalized throughput. So normalized throughput is, that's basically fractional utilization of the link. This is normalized throughput. And turnaround time is the time required for the packet to move from input to outgoing port, delay part. So that also similarly can be estimated here. So what you can do is, t delay multiplied by summation of in each stage probability of its not going out is this. This happens for k minus 1 times, okay. Then it goes out with this probability. So it means the packet is going to in a stage suffer k delay, okay. This is the average value. I am looking at the average estimate, and k can go from 1 to infinity. So this average, once you find out, this I am leaving it to you. I think this queuing theory thing principle you can always use to find out this average value. This will turn out to be pj minus 1, sorry, this has to be j minus 1, because I am looking at in the jth stage at the input how much delay is suffered. So that will be in terms of the previous stage, what's the probability from its output buffer the packet goes out. So that's why it has to be j minus 1. So this is what will be your average value, and of course this is the one stage. So total amount of delay will be nothing but t delay summation over 1 over pj minus 1 tilde, go from j1 to 0 to n minus 1, I think.
This is total delay.
Total delay in the transmission from 0th stage to n minus 1st stage. All stages I have taken. I have done summed up actually. And what's the maximum delay possible is total number of stages into t delay. So you can divide by that. So your normalized delay will be 1 over pj minus 1 over n, that is a normalized delay, okay. That is what will be suffered. So I think with that I close here the buffer delta analysis. The only thing is the results which are need to be seen, but my idea was not to actually discuss the result. Result will always be better if you use buffer delta. An important outcome of this paper was that with one buffer between two stages or two buffers between two stages, after that does not matter. 3 or 4 or 5 does not have any improvement in the performance. So 2 is what supposed to be optimum value, which gives the best performance. The performance is better than unbuffered delta surely. Okay, with slight increase in delay which happens, and this almost become as good as crossbar. See, crossbar is better performing thing than delta because of the blocking. Crossbar does not have any blocking. So you still use a delta, but by using buffering you are able to reach to become as good as a crossbar. So that was essentially the outcome of the paper, but I was more interested in teaching the methodology which was involved, because this is a very generic thing, can be used at a lot of other places also. So I think with that we close on the buffer delta system.